All right.
We were taking up all your time.
That's okay. We've only got one lecture left this week. Okay. So, I am not going to go over this too much, but the last week we went over energy levels and how to calculate them using the Bohr equation, which is a very simple equation that lets you calculate the actual energy levels, like what these numbers are, these potential energies. And the lower the energy level, the lower the potential energy. These energy levels will always start with 1, and they'll count up to infinity, theoretically, until you get to 0 potential energy. That's where your infinite energy level is. Again, it's just a numbering. It's just kind of a label, and we use that quantum number n to label them. Why is this the case? Because unlike Coulomb's law, so remember Coulomb's law, we can plug in a charge for a proton, which is at the nucleus. We can plug in the charge for an electron. And we can plug in any distance we want from the electron to the proton and get a variety of different potential energies. That's what Coulomb's law lets us do. However, and this is a step we're kind of jumping ahead a little bit, at the size of an atom, when you get to really, really tiny sizes, classical equations, which is what this is, and all equations in physics where you calculate, the arc of a ball being thrown, all this stuff, they don't work at the atomic level, okay? We have to switch to something called quantum mechanical equations, which we'll get to. And the reason for that is when you're at these tiny levels, these small sizes, they don't behave like this anymore. You can't just put the electron any distance from the nucleus and get any potential energy. Atoms can only have quantized energy states, meaning the atom could be at this energy, or this energy, or this energy, or this energy, and nothing in between. It's just a weirdness of atoms. That's when you're at really, really small scales, that's what happens. It breaks, what we normally think of as the way the world works. Not coincidentally, but even at the other end of the spectrum, if we get to really, really large scales, our normal equations don't work either. So that's what relativity is. Relativity is working with these really large, light speeds, vast, astronomical scales. So at the small scale, energies are quantized. An atom can only be at certain energies, but not in between here. So Coulomb's law is not perfect, all right? Because Coulomb's lets us have any energy we want. We can plug in any distance and then get any energy. But it turns out we can only have certain energies. And that's what the Bohr equation lets us calculate. It lets us calculate those exact energy states. So you can have an electron at this lowest energy position, which is called the ground state. The ground state is an atom's lowest possible energy state. And then that electron, that atom, could absorb energy through electricity, through heat, through light, whatever method to absorb energy. The electron could jump up to a higher energy state, but not anything, just one of these specific energy levels, and that's it. And then it's in an excited state. So that's in a state of an atom where it's not at its lowest energy state. And then it will drop back down. And when the electron drops back down to the low energy state again, that atom has to get rid of that extra energy. And it'll get rid of that extra energy in the form of a photon. So that's kind of what you did in lab. Well, you built a box that's going to let us measure these photons. For hydrogen, coincidentally, it's a coincidence, only the 3 to 2 transition, the 4 to 2 transition, the 5 to 2 transition, and this one's harder to see, the 6 to 2 transition, these are the only transitions you can see. The rest of them, like here to here to here, these are all too high energy. They make UV photons, photons that are so high energy that they're not visible anymore, or they are too low energy. So over here, the 4 to 3 transition, the 5 to 3 transition produces a photon that is a low energy photon. It's in the infrared area. Yeah?
Is the Bohr's model the En is equal to 2.18?
Yes, yeah, the 2.1.
With the atomic number over n squared?
Yes,
That's
yeah. That, thank you.
How do you spell Bohr?
B-O-H-R. It's also known, here we show it again, because make sure everybody's clear. Because we did cover this.
Yeah, I have it written down, I just didn't
There it is.
write.
That's the Bohr equation. Also, it's actually known as the Rydberg equation too. They're basically just different forms of each other. But that equation, again, lets us calculate the actual energy levels. But the transitions, an electron going from this energy level to this energy level, that's what's responsible for creating these photons, right? And so that's why once you've calculated these energy levels, you need to do a difference between the first, the final, and the initial to get the change in energy. And that change in energy, you can convert it to a wavelength and find the wavelength of a photon. You're going to do that next week in lab. So I'm not going to kind of go over it too much. We saw it last week before the exam. It was a while ago, honestly. But you'll see it again in lab. So, actually, come back off of this.
Just to be clear, the quantum number is something that we're given? Or is that...
So the quantum number is just the labeling of the different energy levels. So for any atom, so for Bohr's equation here, it's going to have quantum numbers, or energy levels starting from 1 all the way to infinity. So you just plug in, okay, for the first energy level, what's the energy of that level going to be? For the second energy level, what's the energy going to be?
Oh, so
That's
it's just a integer.
It's an integer, yeah. So the quantum number is always an integer. It starts from 1 and it counts up.
Okay, very good.
And what doesn't show here very well is the sense of scale between the levels. So if your first energy level is way down here, generally the second one is a huge gap. And then the third one is a much tinier gap. And then the fourth one is an even smaller gap. And it just keeps going. So as you go up in energy levels, the gap difference gets smaller and smaller and smaller. And that's why for the hydrogen element, a transition from 3 to 1 is a huge energy change. So that creates a UV photon. But a 3 to 2 transition is perfect for visible photons. It's the right energy. But then if you do a 4 to 3, that's too small, and it's IR, right? Even if, yeah. So you have to have the right energy to make a visible photon. And it doesn't have to be one energy level. You know, it could do 4 to 2, 5 to 2. Any transition is possible. And in fact, all of the transitions happen. Remember, we're dealing, if you have a sample of hydrogen in those discharge tubes, you've got, you know, Avogadro's number of atoms almost. And some of them might have electrons at energy level 2. Some of them might have electrons at energy level 5. All sorts of different energies for these different hydrogen atoms. And then they're all dropping to different energy levels. So you get every single possible thing happening. Statistically, all of it happens. So that's why you get all the different colors. Okay. All right, so does anybody have any questions about this for now? Because I'm going to skip it and we're going to talk about it in lab next week. So let's. I guess we can talk about this. So not for next week, but for the week after. This is kind of a supplementary thing, kind of off topic. We need to know how to calculate concentrations of solutions. So it's just a really quick kind of tutorial on solutions, just to make sure that we're covered for not next week, but the week after. For a liquid solution. So a solution is a mixture. It's a homogeneous mixture. And those solutions, we're going to have two components mostly. There's going to be a solute. And the solute is the substance, whether it's solid, liquid, or gas, that dissolves in a liquid, if it's a liquid solution. Your solvent is that liquid that you're dissolving stuff into. So a solution is a solute and a solvent. Generally, in general, so not just for liquid solutions, but for any solution, the solvent is usually the one you have the most of. So you have two components. The one you have the more of is considered the solvent. And that's for aqueous solutions, liquid solutions, it's going to be water usually. Okay? But you can dissolve anything in water. You can dissolve a solid like salt. You can dissolve another liquid like corn syrup. Or actually not really a liquid, but or a gas, carbon dioxide. Okay? Which is what soda is.
So a solution, if you were to dissolve copper into a liquid solution, like by a chemical reaction, that wouldn't be a solution in the end if it's all liquid.
Well,
at the end?
copper ion, you mean?
You
Yeah.
remember the very first when we did with the nitric acid and the
Oh,
copper
yeah.
pieces?
So
in lab?
when the nitric acid reacted with the copper metal, it made copper ion. It made copper nitrate. Was one of the products, and that dissolved in whatever water was also there, right? So the nitric acid is water with a bunch of acid and nitrates in it.
Is that a solution?
Yeah, the result was a solution. Yeah, there was copper nitrate dissolved in water. Yeah. But there's, so these are liquid solutions. You can imagine a solution being, anything, a solid and a solid. So an alloy, like steel, is a solution. It's iron is your solvent, and carbon, and molybdenum, and vanadium, and whatever steel is made of. Those are your solutes. But anyway, let's talk about liquid solutions for now. There's your copper solution. Probably copper maybe copper chloride, I'm not sure. Some copper compound, it's usually blue. So you've got solute, solvent, and that's your solution, the result. So, is this a solution? Hopefully you take a look at this and you say, no. I don't know why the answer's not there. And that's because a solution, again, is homogeneous, however you like to say it. You can visibly see two different things. You can see liquid water, or some liquid, and you can see something solid in there. That is heterogeneous, so that's not a solution. A solution has to be homogeneous. At the particle level, what does it mean to be homogeneous? It means that the solute is equally distributed throughout the solvent. All right, so these are clumps of whatever the solid is, not equally distributed. And so when you dissolve salt in water, the dissolution is a physical change, okay? Because what's happening when you dissolve salt, it's sodium chloride, sodium ion and chloride ion in solid form. When you dissolve that in water, yes, the ions are separating, but they're still the same thing. It's still sodium ions and chloride ions. So nothing chemical is happening here. It's just a physical change. All right. So again, here's a visual of sugar being dissolved in water, for instance. You have your solid sugar. All the sugar particles are stuck together in solid form. When you stick it in some water, the water will come in and start ripping apart the solid, not the sugar molecules themselves, basically they'll separate the individual sugar molecules from each other. And so when a sugar molecule is dissolved, that's kind of what you should be seeing if you looked at the particle level. You've got water molecules surrounding these sugar particles, and they're going to be equally distributed throughout the water. Okay. We can say that the sugar molecules are solvated. It's kind of a word that you can use to describe the process here. Salt, such as table salt, is solvated similarly. Again, you've got your solids, so the ions in solid form. All water is doing is separating the little particles into individual particles. That's it. There's no chemical reaction happening because you had sodium ion and chloride ion before. After, you still have sodium ion and chloride ion. Nothing's changing. We're not going to get into it now, but when you have ions, there's no, let's skip it. We don't need to talk about it right now. Okay, so at a basic level, you need to understand what the particle representation of this is. So this is aqueous, right? Whenever something is written AQ next to the symbol of the chemical formula, that means it's dissolved in water. And so if I were to say, what does this look like dissolved in water? Sodium sulfate, this is called. Well, we write it like this for convenience, but if it is aqueous, in your minds, you should be picturing that there are 2 sodium ions for every 1 sulfate ion. That's the ratio. Not that there's just 2 and just 1 of these, but there's a ratio of 2 to 1. And in water, they're in water, there's dissolved. So this ion is being surrounded by a bunch of water molecules. And you don't have to be perfect about how you draw these, but and these sodium ions are equally distributed among all the water molecules. And then there's sulfate ion. And I'm not really drawing what sulfate looks like, but because it's not a big deal at this point. And you basically have this picture repeating because, again, there's going to be many of these ions. But there's going to be a 2 to 1 ratio, and they're surrounded by water molecules. So there's plenty of water out here as well. It's just that the ions are now separate. So that's what this is. Whenever you see aqueous, you should think of these ions as not being together anymore. They are separated. Okay? Okay. Now, let's talk about kind of the point of going over this. We need to talk about concentration. So, there's actually a couple definitions of concentration. The one we're going to use is, in the numerator is going to be an amount of a solute. In the denominator, we're going to talk about the amount of solution. And so what I want to make a distinction between is we're using solution in the denominator, which is the whole thing, not the solvent, which is just part of the solution, like the water part. There are definitions of concentration that do solute over solvent. We're not doing that one. We're doing the one that is solute over total, the solution. And so what amounts are we going to be using? Well, it actually depends. There's plenty of ways to do this amount. You can do mass over mass. You can do volume over volume. You could do a combination, mass of the solute over volume of the solution. There's also parts per million and parts per billion if you're an environmental person. A part per million is it's kind of a scaling of units. Micrograms per gram. That's parts per million. Because the difference between them, a microgram is a millionth of a gram. Parts per billion would be nanograms per gram, or micrograms per kilogram. So the difference there is a billion difference. We're not going to use any of these though, so there's plenty of concentration units, plenty of them. But we're going to be using the one that is called molarity. And I don't know if it's this class, but I did notice somebody is using big M. to represent moles, which is incorrect, okay? Big M has its own meaning, it's molarity. Please don't confuse molarity. If you've taken any bio, you might have heard of molality, which is little m, confusingly. That's a different definition. This is molarity, okay? So, what is molarity? It is moles of solute divided by liters of solution. That's the definition, strict definition. So what I like to remind people is they're going to see a solution labeled, you know, for instance, oh, I've got this hydrochloric acid solution, and it might be labeled 3.0 molar, 3.0 m. So first of all, to read this, I would read it as 3 molar solution. So it's the big M means molarity, but the way you read it is a 3 molar solution of HCl. This is a concentration unit, but in your head you should remember that this concentration is defined as moles per liter. And hopefully you're also thinking, oh, if I have a unit that has a numerator portion and a denominator portion, that's a conversion factor. So whenever you see this, big M, immediately in any kind of math problem, translate it to 3.0 moles per 1 liter. And then, hey, there's your conversion factor. What you can use this for is converting between a volume of a solution and moles of a solute. Right? So let me extend this. Liters of solution and moles of solute. So whatever your solute is. In this case, HCl. That's the solute, and the solution is the entire volume of whatever it is, okay? Of that acid solution. So how do you make a 1 liter? How do you make 1 liter of a 1 molar solution of copper sulfate? How would you make 500 milliliters of a 1 molar solution of copper sulfate? What is the concentration if 3.185 grams of copper sulfate is dissolved in enough water to make a 500 milliliter solution? All of these are valid questions that involve concentration. So, how would you make a 1 liter of a 1 molar solution of copper sulfate? Well, remember that 1 molar is the same thing as saying 1 mole per 1 liter. And so now, how would I make a 1 liter solution? Well, if I need to make 1 liter, I can multiply it by my conversion factor. And basically, this is telling me I would need 1 mole of the solute of the copper sulfate to make that solution. So I would measure out 1 mole. How would I measure out 1 mole? Convert to grams using a molar mass. Figure out what the mass of copper sulfate I need. Weigh it out. Put it in my flask. And then add enough water until you've got a whole liter of solution. That's how I'd make a solution, a 1 molar solution of copper sulfate. So 1 molar, that's the concentration. That's how strong the solution is, basically. How would I make 500 milliliters? I'm going to plug in 0.5 liters here instead. Okay? What is the concentration if 3.184 grams of copper sulfate is dissolved in enough water to make 500 milliliters of solution? So let's do that. If I've got 3.184 grams of copper sulfate, I want to make a concentration. So concentration is moles of the solute, copper sulfate, over liters of total solution. So I need the moles of copper sulfate. So let's convert my grams of copper sulfate to moles. I'm going to use molar mass to do that. All right, periodic table to the rescue. Copper is 63.546. Sulfur is 32.066, and then there's 4 oxygens at 15.9994. 159.6. 1 is enough for right now. And then let's do that math real quick. 0.01994, actually 5 if I round it properly. That's the number of moles of copper sulfate I'm trying to dissolve. And I'm dissolving it with enough water to make a 500 milliliter solution. So I'm going to take that number and divide it by the volume of the total solution in liters. So 500 milliliters is the same thing as 0.5 liters, 3 sig figs, or 3 zeros at the end. So the concentration of this solution is going to be I do it right, 0.039897. So with 4 sig figs, 0.03990 molar, if I round it properly. So that's the concentration of this solution that I just made by dissolving this 3 point something grams of copper sulfate in enough water to make 500 milliliters of solution. Now notice the wording of this question. They're saying we're putting in enough water to make 500 milliliters. Why couldn't you say dissolved with 500 milliliters of water? Yeah, so if you mix that mass of copper sulfate and then exactly 500 milliliters of solvent of the water, together they might actually have a volume slightly greater. So remember, this denominator here is not the volume of the solvent. It is the volume of the final solution. So that's why it's worded the way it is, okay?
We need to know density to actually figure out how much water we need to, or the density of the whatever molecule we're putting in there to know how much water we need, right?
So you could do it that way if you want. But the better way is, well, I don't have a picture of it. In lab, when we make solutions like this, we're going to use these special flasks that have this shape. They're kind of got these long skinny necks, and then they end in a round bottom that's flattened on the very bottom. And there are no markings on these flasks at all, except for one right up around here. And then there's a hole, and there's a stopper you can put them on it. So these are called volumetric flasks, and they are designed for making solutions like this, because what will happen is each of these flasks is sized for certain volumes. So maybe this is a 500 milliliter volumetric flask, and if you put your solid in here, dry, and once your solid is in here, you add a little bit of water, and then mix it up, and then fill it up with water until you hit that line exactly. And once you've hit that line exactly, then you've added until your total solution volume is 500 milliliters. And generally, they have enough sig figs to go to 2 decimal places. That's usually how precise they are. So they're used specifically for making solutions like this. So you basically do the volume after. That's how you don't measure water and mix the water in. Yep. Okay. Very cool. You guys want to try this? I think I already flashed the answer, but how many moles of solute are present in 50 milliliters of a 0.488 molar potassium dichromate solution? Give that a try real quick. And again, the key here is just think of your concentration as a conversion factor.
No one-letter abbreviation for mole, right? It's only MOL as mole.
Yeah, it's MOL as moles, yeah. There's no, yeah, right, no one letter abbreviation. You can prefix mole. There's millimoles, MMOL. That's a very common prefix for moles, yeah. And you can prefix molar too. So millimolar is another one I've seen. Micromolar, actually, I've seen that too. First, when you're dealing with concentration, molarity, your volumes have to be in liters to do any kind of calculations with molarity. So I'm going to convert my milliliters to liters first. And then once I have that, remember that, so I need to convert this volume into moles. Well, I can do that if my denominator has liters, so we'll cancel out. And my numerator has moles, and that is the unit for molarity. Molarity is moles per liter. So 0.488 molar translates to 0.488 moles per 1 liter of solution. And that's it. So 0.05 times 0.488 looks like 0.0244 moles of solute. Now don't forget, we can still do like things like how many moles of potassium ion are in this solution. So not just moles of this solute as a whole, how many moles of potassium ion? So you can then take this moles of potassium dichromate and then do the 2-to-1 ratio to find just the potassium ion, right? So there's plenty you can work from here. Even doing concentration conversions are doable. So what is the molarity of a solution that is 35.05 grams per liter? So, you know, this looks harder than it is, or maybe it doesn't look hard. Hopefully it doesn't. But if I've got 35.05 grams per 1 liter, I mean, all I want to do is convert that grams to moles. And then I've got molarity, right? So how do I get grams into moles? Well, I just cancel out grams and put a mole up there instead. So what is grams, you know, what is this conversion factor? This is molar mass. Grams to moles, moles to grams. So I need the molar mass of potassium chloride. This is the formula for potassium chloride, K plus, Cl minus, which is 1-to-1. So 39.0983 and 35.4527 is 74.551 grams per mole. And magically, I've got it, not magically, but I've got it converted into moles per liter. 0.4701. And this is the same as saying molar. That is exactly the concentration we want. So we just converted that kind of concentration to the one that we're, you know, the one that we want to use. We're not going to do it, I think. Maybe you'll do it on homework. There's, like I said, parts per million, parts per billion. They all have their own way of talking, like, what are the units? And you'll learn a little bit about it, and you'll try it in the homework. But, you know, just think about how do I transform these units to the one I want. So molarity, again, don't forget what molarity is. Molarity is moles over liters. That's what that unit means. There's plenty others you can try. Okay, so I feel like this doesn't have what I needed to have, so I'm going to go back to the other set of slides. We're going to do the end of it. 1 second. We've covered all of this already. Okay. So we're gonna now do. So, any questions about polarity? Hopefully. Okay. So we're gonna switch gears now. Go back to what we were originally talking about, which is structure of an atom, how an atom works, and we're going to look at something called a shell model, and we're gonna kind of come up with it ourselves first. So first, we're going to talk about the experiments that we're going to look at, or the data we're going to look at, and where those numbers come from. So ionization energy, when we measure it experimentally, so not using Coulomb's law, we're not calculating it. If we measure it experimentally, how do we measure those? So it's not an easy experiment to do. You have to start with gaseous atoms. And so just those atoms, so you're doing this in like a vacuum chamber with nothing else around. And then you hit those atoms with high energy electrons. And when we talk about high energy electrons, these electrons have kiloelectron volt energies, which is a lot. So what is a high energy electron? It's an electron moving really fast, like a, an electron moving with the bullet speed kind of thing. And the idea is when this high energy electron hits the atom, the fast moving electron will transfer some of its energy to the atom. And if it's enough energy, it'll cause an electron inside the atom to come out, right? If that atom absorbs enough energy to bring the potential energy up to 0, then that electron that's inside the atom will be able to leave. And so you'll be left with a cation because the atom has lost an electron, and then one of the electrons is now, you have a second electron now flying off. So we actually tune these high energy electrons to find the minimum energy needed to make an electron come out. And that's kind of how we know what the ionization energy is. Yeah?
So I thought electrons only had one type of charge, or like one quantity of charge. Is that not true?
So all electrons have a -1 charge, yes. Is that what you mean?
Yeah, but it says high energy electrons. I don't quite understand.
Oh,
the exact
so
word.
they have the same charge. So charge and energy are different things. So so it's not like the electron has more charge in it. That's why it has more energy. The way an electron that has the same charge has more energy is it's moving very quickly. The faster it's moving, the more kinetic energy it has.
That's fair.
So that's what it is.
Okay.
Okay, so that's what we do, the lower the potential energy of the electron inside the atom, the more energy we need to get it to come out, right? So the higher the ionization energy is going to be. That's just another visualization of it. So again, the closer that atom or that electron is, according to Coulomb's law, the closer the electron is to the nucleus, the lower the potential energy is going to be, and the more energy we have to put back into it to bring it out. So kind of going really deep into the hole, trying to get that electron out. All right, so I'm going to skip this because I think it gives it away. But we're going to first talk about, we're going to look at some ionization energies. And for a hydrogen atom, the ionization energy is 2.178 times 10 to the minus 18 joules. That's for a single atom. But the thing is, a lot of these ionization energies are not written in terms of single atoms. They're written in terms of moles. And so they're going to have different units that we're used to. So before we get to the actual ionization energies of all the other atoms, we're going to start with questions 1 through 3
on page 116, which is the beginning of Chem Activity 4, just to kind of orient ourselves what these new units mean, okay, and how we come by them. Board 16. So just do 1 through 3 for now. 5 minutes. We'll come back. See if I can find where they are. There we go. So here's 1, and then 2 and 3 in the next page. Yeah.
Would it be doubling this energy?
Exactly, yeah. So you need 2 of them to come by 2 different atoms, so you can double the energy. Yeah.
So, this first one was ionization energy to purchase 2, but we just double it?
Yeah, that's it. Yep. The third question is the interesting one. So when you get to it, based on what we've learned so far. No. I'm curious. I want to hear everybody's explanations. They're all invariably going to be a little wrong because we don't know enough yet, but it's fine. wanted people to at least get through the first one so that the new units don't throw you off too much. So 1 atom takes this much energy. 2 atoms would take double the amount of energy. If I had a mole of atoms, and again, people still, not everybody, but some people still have a bad understanding of moles. A mole is just a number. It's like dozens is 12. A mole is just a big number. So if I have that many a mole, which is 6.022 times 10 to the 23 atoms, then I multiply these two together and I will get a ridiculously large number, 1311591.6 joules. And so that is the energy I need to ionize a mole of hydrogen atoms. But this is a really big number, so it might be nicer to use megajoules. And so megajoules, if you don't know the conversion, is 10 to the 6. So joules to megajoules. 1 megajoule is 10 to the 6th. It's the next step after kilo. And so this becomes 1.3 4 sig big, so 1312 megajoules is the amount of energy it takes to ionize 1 mole of hydrogens. So you could also say per mole of hydrogen. That's the energy per mole of hydrogen atoms. Okay? So we're kind of redefining it at the unit at the end there. But so that's where these come from. And so for number 2, for atoms with many electrons, not all electrons are at the same distance. In which case, in this case, which electron with the lowest ionization energy? The one that is closest to the nucleus or the one that is furthest away? Which one? Furthest, yeah. So according to Coulomb's law, the larger the distance, that's in the denominator, the larger the distance, the smaller the potential energy, the closer to 0 it is. And that means the smaller the ionization energy is going to be, right? So potential energy and ionization energy are inversely, or not inversely, they're opposites of each other. Or let's maybe this way, let me write it the other way. Makes more sense. In my head at least, even though they're the same. So if this is small, that's going to be small. They just happen to have opposite signs. Okay. So the smaller the potential energy, the closer to 0 it is, the least negative it is, the smaller the ionization energy is going to be. So the furthest away electron is going to be easiest to ionize. Now, this is an interesting one. If you have to graph ionization energies versus atomic number, that's on the x-axis here. So atomic number, what would you predict based on what we've learned so far? I saw a couple different graphs. Anybody want to explain why they think what they thought?
Sure, I'll give mine a go.
Okay.
So I put a number of horizontal lines, and they decreased in a logarithmic sort of look.
Yeah, like that sort of.
Yeah.
Why did you think that?
Well, I figured as you go down the periodic table vertically, the electrons, they sort of fill up and they get farther away from the
Okay.
nucleus.
That's a really good guess. So you're applying future knowledge, but that's okay. It's okay. So basically saying as you get higher in atomic number, go down the periodic table, the electrons get further away. And that's why the ionization energy might go down. That's a fair assumption. Anybody have another one? I'll tell you what I would think if I knew nothing else. So according to Coulomb's law, the potential energy, which is the opposite of the ionization energy, so let's just talk about the size of it. That's the size of the ionization energy. If the distance to the electron, to the nucleus is the same, and we don't know too much about that yet, but let's just assume the electrons are all about the same distance. Well, what else is going to affect the size of the potential energy? It's the charge of the nucleus. So what happens as atomic number goes up?
Charge goes
The charge of the nucleus increases. You get more and more protons. So as you get to higher numbers of protons, the ionization energy, I would think, would go up, because you would get a much more negative potential energy and so a much higher ionization energy because of that Q1, right? It keeps going up and up and up and up. So the potential energy is going to get bigger and the ionization energy is going to get bigger. So that's what I would think if I didn't know anything about the distance. Like, I don't know where the electrons are. If they're about the same distance in all cases. But that might not be the case. So this is what we're going to figure out.
Can you, before you go on,
Yeah.
can you go back to number 2? I started at 1, and I said the electron closest to the nucleus has the lowest. What-
So, okay,
Huh?
the closer it is, the lower the potential energy is going to be.
Right.
So on the potential energy scale, here's 0. Yeah, the closer it is, the lower, the more negative the potential energy is going to be. But the lower that potential energy is going to be, the bigger the ionization energy is going to be.
Okay.
Right? So yeah. So if it's further away, it will only go down that far, and then the distance to get back to 0 is much smaller. Does that kind of make sense?
So the electron furthest away from the nucleus has the lowest. Is that what you were saying?
Yeah. Okay. Here's a visual that maybe helps. Think of 2 magnets, and you're holding them a certain distance away from each other. You know, if you get this close, you can pull this one away very easily. But if you put them really close together, it gets a lot harder to pull the magnet away.
Yeah.
And ionization energy is the effort you need to put in to pull it away. So when they're far away, easy to remove the other one. But when they're close, it's really difficult to remove that magnet. Okay?
Okay.
So ionization energy is the effort you need to take to remove that electron. And the lower the potential energy, the more effort you need to remove it. So the one that's further away is easy to remove. So low ionization energy. Okay. So here is the meat of this problem. We have a list of ionization energies. And I don't want to give anything away. I want you guys to look at them and answer the questions. 4 through 10, not just the first 2, I think. Just keep going. So 4 through 10. And we'll spend about 10 minutes just trying to answer some of those questions and just kind of see what you can see based on this data. What conclusions you can make. Yeah.
Trying to keep up the higher the proton energy in for the atomic mass would
Or
mean
the number of protons. So the more protons you have, the more positive charge there is, right?
yes.
And then according to Coulomb's law, that Q1 is going to be the charge of your nucleus, right? So
Yeah.
the bigger this number is, this is going to be super low, super negative. So if all you knew was about, hey, this, and you didn't know anything about this yet, the higher the number of protons, the higher the ionization energy is going to be, because your potential energy is going to be super negative. And that's why in the graph, you just get that line that I just drew like this,
Okay.
where it just goes up. The more protons you have, the higher the ionization energy is going to go. Now, this is wrong, but this is a prediction based on limited information we have right now.
Okay.
We're pretending we're like, don't know much about the atom when we're discovering everything ourselves, basically. you can ask questions if you want.
I was gonna say the more electrons it has, it seems like it's harder to get rid of them, but also there's more protons, so I don't actually understand that relationship yet.
Yeah, we'll get to it. Yeah. If you when you see it plotted, it'll make a little more sense. If you see how the pattern works.
Right.
And another clue I'll give you is the periodic table has a lot. The organization has a lot to do with what that data looks like. Oh, yeah.
For Friday, could just be the charge.
Yeah.
Okay.
Yeah. +2 versus +1.
Yeah.
Like we've answered this before.
Yeah, exactly, okay.
Yep. Okay. So what is the other variable we want to adjust? The distance. So maybe there's something different about the distance of the electron. So even though the charge is so much larger, maybe that third electron. And that travels to the out places, so maybe that is well, with helium it would be closer, and with lithium it would be further away. Okay, yeah. All right, I think we can talk about this together now. So this is my rough sketch of this data. If you look at the ionization energies as you increase the atomic number, it goes up, and then after helium it drops, and then it goes up again from lithium to neon, and then it drops when it gets to sodium, and then it goes up again from sodium to argon, and then it drops, and hopefully you notice that it kind of follows the periodic table rows. So there's big differences in kind of what we naively, or at least I did, predicted. You got it a little bit more right than I did. But, so let's kind of explore why this is. Why is it doing this stair step? So, and what could be a reason for it doing that? And so 5 is kind of explaining, well, let's just look at two things at a time. So why is helium's ionization energy greater than hydrogen's? We've answered this question before. Helium has a +2 at the nucleus. Hydrogen only has a +1. So helium's potential energy is lower, and therefore its ionization energy is higher, just because of the charge. But that doesn't fit why lithium is lower. If we were using that explanation for lithium, we would think, oh, it's even higher than helium. So according to Coulomb's law, at least, the only other variable we haven't talked about yet is the distance. So lithium's +3 should make this numerator much bigger than helium's numerator. But the fact that the potential energy for lithium is higher, it's not as negative, because it's got a lower ionization energy, must mean that the electron, the third electron that lithium has now, is further away. That third electron from lithium that you're adding is not at the same distance as the other two. It is further away from the nucleus, and that's what makes it easy to remove. That's what makes the ionization energy of lithium so low. So this is the beginning of what we call the shell model of the atom. So electrons are arranged in these shells. And if you want, you can think of them like planets orbiting a sun kind of thing. It's not a correct visualization, but it's a simplification that works in this case. So here's a shell model for hydrogen. We've got a nucleus with a +1 charge and then a single electron. And here's a shell model for helium. We've got a nucleus with a +2 charge and 2 electrons in that shell, that first shell. Let's see what else. I think that's yeah. So the value of the ionization energy is described as being consistent with the model in which the 2 electrons in helium are in a shell. Use the Coulomb equation to explain how this conclusion could be reached. Well, we've been using this the whole time. Okay, so if you look at the energies for helium and hydrogen, helium is not quite, but close to being double the ionization energy for hydrogen. And so that would make sense. Hydrogen has a +1 for Q1, helium has a +2 for Q1. And so if their distances for the electrons are similar, yeah, it's almost double. So that's why the ionization is close to being double. It's not exactly double, but it's close. So that makes sense. Now, question 7 is, well, let's examine what the shell model would look like for lithium. And so, if all 3 electrons in lithium were in the first shell, similar to the way hydrogen and helium are, so what they're saying is if lithium looked like this, with a +3 at the nucleus, and only 1 shell of electrons, and all 3 electrons for lithium were in that first shell. So that's the answer to question 8. Or actually, no, that's, well, okay, that's 7 and 8. This is the diagram we would need for 7 and 8. What would make sense for an ionization energy for lithium if this was the case? Yeah, it would be much bigger than helium's. If that third electron was in the same shell as the other 2, and it was attracted by a +3 charge, it would have a much higher ionization energy. We would predict, somewhere around 3.6 megajoules per mole, triple what hydrogen's is. Okay. But that's not the case, because in reality we don't see an ionization energy for lithium like this. We don't see 3.6 megajoules per mole. What we see instead is, was it 0.6? Go back real quick. There it is. 0.52. It's really low, lower than hydrogen's. Okay. So that's incorrect. That's not the model for lithium. Another student proposes that lithium has 2 electrons in the first shell, and then there's a second shell that is further away, and the third electron is in that second shell. Why would this work? Well, now if we're ionizing this electron, if that's the one we're removing, the distance to the nucleus is much bigger. You have a bigger denominator, so your potential energy is going to be closer to zero, more positive, less negative, and the ionization energy is going to be a lot smaller. So that's what the way you should think of lithium. Lithium has a shell model that has two shells with 2 electrons in the first shell and a third electron in the second shell. And one more. There it is. There's our fancy picture. By the way, where you draw the electrons on the shell itself doesn't matter at all, as long as they are on the correct shell. Okay. Based on the model, would the amount of energy required to remove one of the electrons be greater than, less than, or equal to the ionization energy for lithium? So what they're saying is, okay, well, let's focus on not removing this electron. What if we try to remove this electron instead? How much energy would we need to spend to remove that electron? A lot, because it is closer, and it's still being attracted by a +3 charge. So this electron has a much lower potential energy than this electron does. So we need a lot more energy to remove this one. This one is the easier one to remove. It's further away. But the definition of ionization energy is removing the easiest to remove electron. That's it. So this one's going to come off, not the inner ones. All right. So here is a better graph than what I just drew. And the trend isn't perfect. I mean, the ionization energy goes up, but there's a little bit of, inconsistencies in that row. But notice that, this is a row in the periodic table. Lithium to neon is the whole second row. Sodium to argon is the whole third row. And then potassium to calcium, it's the whole fourth row. So what is happening here is that the ionization increases, and then when it drops, what's happening is you're starting to put electrons in a new shell. So lithium marks the beginning of adding an electron to the second shell. And we keep adding electrons to the second shell. But the ionization energy goes up because we're also adding protons to the nucleus. But then all of a sudden, after neon, the ionization energy drops again. We're still adding protons, but now the electrons are being added to a new shell, a third shell. So we're adding electrons to a third shell. Boom, we've dropped to a fourth shell now. That's the pattern here.
So for Coulomb's law, the charge of the electron is always going to be -1. So ultimately, it doesn't really matter how many protons are in the valence shell. The only thing that changes for the ionization energy in the same row on the periodic table is the number of protons.
Yes, sort of. Yes.
Yeah.
We're making a very big simplification, though. And that is, what do 2 electrons do?
Okay, that's, yeah.
So 2 electrons are both negatively charged, and 2 electrons repel each other. So we're going to include that eventually, but right now we're making it easy. All right. So, all right, we talked about these. This is the answers to the questions we just went over. So I'm just going to blow through these. Feel free to look at the slides yourself if you want to step through them a little slower. So, what is the answer here? So, based on this data, how many shells should potassium have? Did it even start? Let's see. Oh, you know what? Hold on. For some reason, it never started. There we go. So, we talked about this, like how this works using the data. I think split? The answer is D in this case. So you follow the data, you can say, well, we're adding to the first shell here. Boom, we're adding to the second shell here. We're adding to the third shell here. Potassium is where we start adding to the fourth shell. But there's this even easier way to do it. Look at where potassium is in the periodic table. It is the first element in period 4. And that's where the fourth shell starts. We start adding electrons to the fourth shell. And the periodic table is laid out that way on purpose. So notice, there's only 2 electrons in the first shell. It's not a coincidence there's only 2 elements in the first period. Hydrogen, helium, that's it. And in the second shell, we have, we haven't seen the pattern yet, but there's 8 electrons you can put in. There's 8 elements in there too. Yeah, question?
I got this from like your previous contributions. I was gonna say, I think you kind of answered it, but just to make sure like that's the answer. I pressed C because like I thought each shell has 8, but the first one has 2, so that's why it's not. The first shell has 2 instead of 8.
Yeah, that's true.
So that's why it's 4 instead of 3.
Well, so potassium has 19 electrons.
Yeah.
So 2, 8, 8 is 20.
Yeah.
Sorry, 18, excuse me.
Yeah.
And so that last missing electron has to go in the fourth shell.
Yeah, so but I was just thinking like all of them have 8 and I forgot, so that's
Okay.
the reason why.
That's fair.
Okay.
Okay. So, how you want to think of the shell model is up to you. There's various ways. I think this diagram model is pretty easy. It's a nice, simple way to do it. But if you want to think in 3D, it's okay too. But that's the idea of the shell. It's all not quite the right way to think about it overall. But for these simple cases, it's okay. Okay? And like I said, the shell model, so the number of shells an element has electrons in corresponds to the period they're in. So you just look at what period they're in. That's how many total shells with electrons they have in them. All right. Now, as far as numbers of electrons that these shells can hold, there is a pattern. And like Dean was saying, first shell holds a maximum of 2. The second shell holds a max of 8. I'm hand waving here a little bit. The third shell does hold 8, although it gets complicated when we start talking about transition metals. And this is actually not right. The fourth shell, we're not going to limit how many electrons it has because we stop counting. We're not going to use this pattern once we get past the main group elements. So generally, when we're talking about easy elements, patterns that repeat, the main group elements, which are these and these, the ones we focus on, and really only the first 3 rows. After once you get to the 4th row, it starts getting really complicated because that's where the transition metals start. So I would put a question mark here. It's not exactly 8, but these, yes, 2, 8, and 8, okay? And if you forget, look at the periodic table. It tells you how many elements are in the first row. 2, 8 in the second, 8 in the third. Okay. Now, yeah, so it's a little different for transition metals. We'll get to those eventually. So you're responsible for, drawing these shell model diagrams. You should be able to take any element, or the little simpler ones, and come up with a shell diagram for it. And the basic shell diagram is number of protons, in the nucleus, and then add electrons. Remember, the electrons match the number of protons, unless it's an ion. We'll get to those too. But for neutral atoms, the electrons match the protons, and then just add electrons until your shells have the right number of electrons. Okay. So, a couple definitions. When you draw the shell model, the outermost shell, there might be only one shell, but whatever that outermost shell is, that's called the valence shell. It is the most important shell because that is the shell that is facing all the other atoms that it could react with. The valence shell is the most important shell in chemistry. How do you know how many, what valence shell is? look at the row the element's in. So for potassium, the valence shell is shell 4. For sulfur, the valence shell is shell 3. Now, valence electrons are the number of electrons in that shell. So for lithium, there is 1 valence electron, because there's only 1 in that outermost shell. For neon, there's 8 valence electrons. Valence electrons are also easy to figure out if you look at the periodic table. Look at the group number they're in. And group number, I'm talking about the black one, the one with the Roman numerals. So oxygen is group 6A. So from the group number, I know that oxygen has 6 valence electrons. And if I wasn't sure, you can just do the shell diagram just like that. Oxygen has 8 total electrons, so you start filling the shell. 2 in the first shell, I've got 6 left, 6 in the second shell, that's it, 6. Yeah?
The valence electrons are also what decide the atom of oxygen can react with, like what other atoms it can react with, because it has to be
Somewhat,
able
yeah.
to, it has to fulfill its valence shell, balance out neutrally, and it can only react, can oxygen react with everything on the periodic table? Or is it just
yeah, kind of. So we're going to get to it. The valence electrons is very deeply tied into the reactivity. So we will eventually learn something called the octet rule. Most elements like to have 8 electrons in their valence shell, and if they don't, they will somehow get them, and that's what causes reactions to happen. We'll get to that. But yeah, the valence electrons are the most important electrons in an atom. So lithium tends to be highly, highly reactive. In fact, every element that has 1 electron in its valence shell tends to be reactive like lithium is. And that's pretty much everything in group 1. These are all metals that pretty much explode when you put them in water. Neon is a noble gas. It has 8 valence electrons. It's not a coincidence. Every single noble gas in that last column, except for helium, has 8 electrons in its valence shell. Somehow 8 valence electrons makes it inert, makes it unreactive. So, this valence electrons, this is a clue right now to how reactive something's going to be. We're going to get to why. We need a few more tools in our toolbox to start to develop this idea. Okay? And that's where this thing called core charge comes in. So, we have our shell model now. That's not enough. We're gonna process the shell model to come up with this new thing called the core charge. Think of it as a tool. It's just a tool for help us understand how an element might behave. So, the idea behind core charge is that we understand electrons actually repel each other. So when you have an atom that has multiple electrons, like lithium, these 2 electrons repel each other. These 2 electrons repel this outer electron. And all of those repulsions are going to affect how attached that outer electron is to the atom itself. It's going to affect its ionization energy. So Coulomb's law is very limited. Remember, the whole point of Coulomb's law is 2 particles only. That's it. Proton, we usually do the nucleus in the middle because it's one big lump, and 1 electron. But now we have these multi-electron atoms. So how do you do Coulomb's law when you have 3 or 20 electrons? So this is where core charge comes in. We're going to simplify our model. And what we're going to do is we're going to combine the inner electrons and the nucleus into 1 number to represent an overall attraction. So the core charge is the net overall charge from the core, the inner core. And so in lithium's case, the valence shell is separate, but all of the inner shells and the nucleus we're going to combine into 1 number. And it's pretty simple, because what I'm going to do is I'm going to take the protons, which is the +3, and I'm going to subtract the inner electrons, because each electron is -1. So a +3 and a -2 gives this an overall +1 core charge. So I'm not going to write this normally, but that's the core charge now. And we didn't do anything with the valence electron. That's still the second shell with 1 electron. So this is the shell model. Ignore the red line, that's not really there. This is the shell model, this is a core charge model. So all we've done is combine the inner electrons and the nucleus together. So what does this electron feel? Overall, it feels a +1. Why? Because in addition to the +3 attraction, it's feeling repulsions from these 2 electrons. So it's a combination of the attraction and repulsions together, giving it an overall +1 core charge. That's what core charge is. So, like I said, it's a tool. We're going to use it to explain things. So we need to compare it with other atoms for it to kind of make sense. So there's lithium. There's the shell model for lithium. There's the core charge model for lithium.
I had a question.
Yeah.
When you were explaining this before we got into core charge, I was thinking that that the electrons repel each other.
Mhm.
Like, so they're coming together, but they're still kind of like repelling each other until that little hole that's left, or those holes that's left by not a non-filled valence shell, the electron that is repelled from this electron actually is more attracted to the nucleus inside of the atom itself because it's positive, and it fills in that hole to attach to the nucleus. Does that make sense?
I think I know what you mean.
It's kind of like,
But
but that's not what it is. That's just the thought that came into my mind.
that's so one thing you have to keep in mind is that the fact that I drew the electrons here means nothing. Like these 2 electrons, and so this is why they planted around the sun model. The orbit model is not very good. The true picture of what the electrons, where they are, is everywhere all at once. So you can't say there's a hole somewhere because, so I mean it's a fair idea, but it doesn't match up with what we know about the current model with the electron, which we haven't gotten to yet. We're still in a very simplified version of it right now. So, but yeah. Just to make sure, if I have oxygen, how many inner shell electrons does oxygen have? So if you drew the shell model, how many inner electrons does oxygen have? We need to draw it. We'll draw it in a second. All right. So votes are all over the place. So for oxygen, it has 2 inner electrons. So again, we have to define, before we think about the inner electrons, we have to know what the valence shell is. This is the valence shell for oxygen. It's the outermost shell that has electrons in it. And so everything else is an inner shell. So if there's anything else, there's these 2. And that's it. 2 electrons in the inner shell. Wrong one. So, how many valence electrons does oxygen have? Hopefully this is an easy one. Okay. Instant answers.
I'm changing my hand.
Okay, go ahead. There we go. So it's got 6 valence electrons. All right, and you can just count them. Or you can look at the periodic table. Oxygen's group 6A, 6 valence electrons. Okay. So what is the core charge going to be? 6 valence electrons, 2 inner electrons. Core charge is what? How do we calculate that? So, answers all over the place. That's expected because we haven't really gone over this in detail. The core charge is going to be 6. It comes from the fact that, oh, it's not there. It comes from the fact that you're taking the number of protons, which is 8, and subtracting the inner electrons, which is 2. 8 minus 2 is 6. There's a pattern here, if you've seen it, but we'll talk about this. So, based on the information from an oxygen atom, what do you expect the core charge of sulfur to do? Let's just take a guess. What do you think it might be? You can calculate if you want, but. All right. All over the place. So, we've got B, C, and D. The answer here is 6, just like oxygens. So why is it just 6? I mean, we can calculate it really quickly. So let's do the shell model for sulfur. It's 16 protons at the nucleus. And then it's got 16 electrons. So 2 in the first shell. Not enough. We're going to fill the second shell. It's got 8 total. That's the pattern. 8 possible. Still not enough. 1, 2, 3, 4, 5, 6, 7, 8. So I've got 10 electrons. I need 6 more. So our third shell is going to have 1, 2, 3, 4, 5, 6. And then we'll do nucleus, nuclear charge, minus inner electrons. So now there's 2 shells that are inner shells. That's the valence shell. So this has 8 plus 2, 10 total inner electrons, which is plus 6. Now, if oxygen is plus 6, sulfur's got a plus 6 core charge, selenium probably has a plus 6 core charge. Notice that oxygen and selenium also have 6 valence electrons. So there's a pattern there. For neutral atoms, the core charge will equal the number of valence electrons. It's an easy way to figure it out. You don't have to calculate it this way. For neutral atoms only, the core charge matches their valence. So this was lithium, right? Plus 1 core charge, 1 valence electron. Same number.
How do you know if it's neutral?
You have to be told. You have to assume, like, if it's not told, assume it's neutral. But if it says lithium ion, then it's lithium plus with a missing electron.
So the core charge is the same as the amount of valence electrons?
Mm-hmm.
Okay.
Now, we don't have time to do the next activity, but core charge is, again, it's a tool for helping us understand in a very simplistic way how, like, what is the attraction of this electron, this outer electron, to the rest of the atom. So, like, we have to consider both the nuclear charge that's attracting it and the electrons, inner electrons that are repelling it. And we can't use Coulomb's law because it's too simple. It only does 2 particles. And so one technique, again, is to use something called core charge. It's a way to very simply kind of estimate, well, what is this outer electron really feeling? This is, like I said, it's a very simple tool, one we're going to use to great effect. But in general, the way you would calculate what does that electron feel, what is the effective atomic charge that this electron feels, you have to consider a lot of other things. And overall, this term that kind of subtracts from the actual nuclear charge, so for us we use just the number of inner electrons. But the general name for that term is called shielding. And the way it works is, hopefully it's obvious. These electrons, these inner electrons, are shielding the outer electrons from the nucleus. They're preventing the outer electrons from feeling the full force of the nucleus. Right? Because this nucleus, whatever it is, has a positive charge. it's attracting this outer electron, but these electrons are at the same time repelling them. And so this outer electron is being shielded from the nucleus by these inner electrons. Now, there are many, many ways to calculate this shielding concept. It's beyond what we're going to do. And like I said, core charge is a very simple tool for us that we can use to represent this shielding. Okay? Or core charge is the Z effective, I should say. It's like, hey, what does it actually feel? But if you ever see that term shielding, that's what it is. It's that combination, or it's the inner electrons repelling the outer electrons. It's preventing the outer electrons from feeling the full charge. Okay. I don't want to get into the next activity, but I kind of want to give you an idea of why core charge is so interesting. And I guess the first one I can share with you is looking at the difference between lithium and neon. So neon has a +8 core charge, and then it would have 8 valence electrons. So why is the core charge model so so useful? I mean, immediately, hopefully, you can understand ionization energies between these two. So what is an ionization energy? Is how much energy to remove the easiest to remove electron. So it's always going to be a valence electron that's removed. This valence electron in lithium is being held on with an effective +1 charge. Whereas these electrons are being held on with a +8 charge. And so, without having to look at the more complicated picture of the shell model with all these electrons and the distances and all that, what we're seeing is, it's pretty clearly, this is being held on very weakly compared to this. This is being held on with a +8 charge. So that's going to have a much higher ionization energy. This has a much lower ionization energy. And just from that, I mean, we can now predict things like, well, I expect lithium to lose its electrons very easily. And it does. Any chemical that comes into contact with lithium has a very easy chance of stealing its electrons. That's what water does. When I dump lithium metal into water, water will very easily take its electrons away, react with it. Neon, however, these electrons are held on rock solid. Neon does not want to get rid of its electrons. So it's not going to react with most things. It's an inert gas. It doesn't really do anything. So this is what I mean by, we're having all these tools. We're going to use these tools and this understanding of the shells and the electrons to kind of predict how it reacts with things. Yeah?
How do you get neon to react in neon signs then? If it's...
So it's not reacting. You're just feeding it some energy, and it's absorbing the energy and then spitting it back out as a photon. That's it. So there's no chemical reaction happening, so no particles are changing. So it's staying neon. It's just taking some energy in and then spitting it back out as light, as a photon.
Nice. So it's a physical change.
Yeah, absorbing energy and releasing energy. Yeah, that's it. Yeah.
That's a physical change?
Well, yeah. So you probably learned in intro chem that a change of energy is evidence of a chemical reaction. It's not always a chemical reaction. So whenever if you see something change temperature, that wasn't because you applied flame or something like that. A change in temperature is generally indicative of a chemical change that's happened. But it's not proof. It's just evidence. So, hey, the temperature changed. There's been an energy change. It must have been a chemical reaction. But not in neon lights. Neon lights, you're feeding it electricity, you're feeding it energy, and it's spitting out photons. That's it. No particles are changing, which is what you need to have a chemical reaction. All right, I'm going to stop here. I think we're a little early, but I'm going to stop here, and we'll pick it up next week. So we're going to expand our shell model. We're going to introduce subshells, which sounds like, oh my God, more complicated, but it's going to evolve into something hopefully you've seen before in like a high school chemistry or something class. Yeah. Oh yeah, I mentioned it to other people. So I have 2 pages left to grade, so I should have it done if I work on it on the weekend, I should have it done this weekend. I might wait till Monday to do it, but we'll see. All right.
That sort of answers my question, cause I was gonna ask you if
Oh,
you were
please,
grading
yeah.
it